before the talk, I have a very short announcement. So, as a continuation of the cultural life that Ola organized for us, tomorrow evening we're going to have dinner, some social dinner. Unfortunately, we don't have financial support for this, but the place is really nice and affordable, so I really recommend it.
What place?
Georgian kitchen, and but to make reservation, we must know in advance at least an approximate number of people. So if you already understand that you will go for this dinner, can you raise your hand? Yeah, 1, 2, 3, 4, 5, 6, 7. Yeah, 14. Thank you. Thank you very much. So I'll announce it once again tomorrow about the time of the meeting and everything. So thank you.
Okay. The last speaker today is Roland Abuaf. The title is Hyper-Kähler categories.
Thank you. So, first of all, I would like to thank the organizer. They've been very helpful with me. I had some problem with my visa, and still they were able to do everything in a quite short term. So I'd like to thank them for that. And I'd like to say how I met Fyodor. So, a few years ago, I was a master's student with Christian Peskin. And he told me, there is an interesting book I haven't read in full details, and perhaps we could have a look at it, and we can discuss about it. So this is how I first met Fyodor. In fact, for me, Zach was not a person, but it was a book. It was a book, Tangent and Secant in algebraic geometry. So most of us will probably agree it is one of the most beautiful books on projective geometry. And as we know, too much beauty can be dangerous. And indeed, I thought I had a ruptured aneurysm while I was reading his proof of the classification of coarse varieties. But finally it wasn't, and I survived, and I was lucky. So a few months later, I was even luckier because Peskin invited Fyodor in Paris for a few weeks. And so I was, of course, quite stressed to meet this god of projective geometry. But when I finally there talking to him, so I was, of course, struck by his ability to see and explain geometric phenomena that one could have never dreamt of. But I was mostly struck by his generosity. And in fact, it's what keeps on striking me over and over with Fyodor is that he's extremely generous with time and with ideas. If you have a question or an idea, you can always discuss that with him. And even if the question is very naive, and even if you are Salieri, you can discuss with him, he will not say no. And so sometimes the mathematical world of Fyodor is described as a small garden, but with very colorful flowers of intriguing size and shades. And even these flowers can be dangerous if you try to grab them alone, but fortunately enough, Fyodor is always here to give you one if you ask him. So I wish you a very happy 65th birthday and many more flowers to come. Okay, so perhaps the subtitle of my talk would be the categorical Salieri wants to be Mozart. So I want to explain what should be a Hyper-Kähler category. So we start with X, smooth projective. And T will be an admissible category, a full admissible category in DBX, so it's an orthogonal component. it just means that it is a full subcategory and it is endowed with right and left adjoints. So I would like to give the definition of T being Hyper-Kähler. So why do I want to do so? Well, there are many reasons. So the first reason is that Hyper-Kähler manifolds are very rare. So, in fact, except in dimension 6 and 10, we only know two types of deformation of such manifolds. And on the other hand, we have absolutely no idea how to classify them. For instance, in fixed dimension, say even 4, it's not even known if there are finite type of deformation of such objects. So they are quite intriguing because we don't know if there are finitely many types of deformation, but still we are not able to construct more than 2 in most dimensions. And in fact, one observed that while constructing such manifold, we know very well how to construct many examples of singular ones. But the fact is that one would like to smooth them in a way which would preserve the symplectic form or the Hyper-Kähler properties. But it's very hard to do so in the commutative world. It's almost always impossible. But it seems, so I'll tell you my experience, that in the non-commutative world, it seems more likely that one can find a way to smooth this singular Hyper-Kähler, to smooth them in a non-commutative world. So basically, smooth singular HK in a categorical way. I will try to make that more precise later. Well, and the second reason is that there is a result of Verbitsky saying that Hyper-Kähler manifolds are self-dual for mirror symmetry. So, as you know, there are many different statements for mirror symmetry. So, Verbitsky proved one of them, and in one of his statements, he proved that such Hyper-Kähler manifolds are self-dual for this symmetry. So, if one believes in Kontsevich conjecture of homological mirror symmetry, one expects that dB of HK manifold should be very interesting. I will not enter in much detail why that should be interesting, but there are objects to be studied as categorical objects. But as I said before, we know very few of them, so it's very hard to test if they are really interesting or if it's just by chance that we have so few examples they happen to be interesting. But anyway, so perhaps as we are dealing with categories, what is interesting is not so much the manifold itself, but its derived category. So if one can produce triangulated categories which look really much like derived category of Hyper-Kähler manifolds, perhaps they would show the same features as a derived category of Hyper-Kähler manifolds, and perhaps we can test Kontsevich conjecture. So it's also a way to have further example to test some conjectures coming from mirror symmetry. Okay, so I was lucky enough because we have talked a lot about Hyper-Kähler manifolds, and many talks mention them, but no one defined them, so I can give the definition I want, and no one will contest. So X is said to be HK manifold. So say projective HK manifold if X is a smooth projective. If the canonical bundle of X is trivial, and if so some algebra constructed from the cohomology of the structure sheaf is of specific type, so it's Ct divided by T, sorry, manifold of dimension 2n. So if it is T n plus 1 with T in degree 2. So looking at this definition, one can wonder, so how to categorize this. So this is, well, this is not too difficult. There are now standard definitions to do that. This is also the now standard way, using self functors to do that. So the last thing is to remember this condition. Basically, this is this condition that we want to put in a categorified version. No, so before jumping into the problems which might be related to the definition, I want to, well, because probably my talk is less isometric than the one we have had, so I want to highlight a few questions which are perhaps general enough so that everyone can get interested. So the first question is how to define HK manifold, HK space at the categorical level. And you see from this definition, or from
I want to give an answer.
Sorry?
I want to give an answer to this question.
More or less. Yes, so, but perhaps not the answer you expect. So, looking at the definition, this definition, or other definition you might know, the first naive way to do that, we would say, I just have to find odd numbers, even odd cohomology, for a nice triangulated category. And a sub, if you look at this, sub question, sub problem is, of course, proving that odd numbers are derived invariant. That is, if I have two varieties which are derived equivalent, then they have the same odd numbers. If I want to give a definition for a category which is quite reasonable, I need, well, if I am too naive, if I want to give a definition of odd numbers, then I have to at least to verify that they do not depend on the representation of the category. Of course, it's a very hard problem, and I don't want to jump into the full problem, because otherwise I will never be able to give a definition. So the second question is, so how to construct new examples of Hyper-Kähler spaces. So by spaces I mean non-commutative spaces, not only commutative one. One, depending on the definition, so of course, still I don't know the definition, it's difficult to produce a space for which I don't know how to define, but depending on the definition, this should be this should be at least less difficult than in a commutative world, because we have more techniques to smooth spaces in the categorical world. So, as I said before, one of the obstructions to construct Hyper-Kähler manifold are singularities. And in the commutative world, we don't know how to resolve them in a good way. So, as we know how to resolve them in the categorical world, one might hope that if the definition is well formed enough, it will be possible to construct much more examples. Okay, so this should be in some sense one of the easiest steps. Well, and the last step is that what are the properties of this category? Of these categories. So if X is a commutative Hyper-Kähler, then we know that its tangent space is isomorphic to its cotangent space. So using for categories, there is a cohomological theory, which is called the Hochschild cohomology. Well, I will not define it, but in that special case, we find that this categorical cohomology theory is isomorphic as a ring to the Betti cohomology. And furthermore, we know that this. Sorry?
It's not gradient.
No, it's good.
The different.
Well, perhaps the grading is shifted.
Just one is vertical, not this one.
No, but I mean, it's special case. It's a special case when it's Hyper-Kähler.
Yeah, it should.
No, still there is a rotation of the approach there.
Yeah, but for
Yeah,
Hyper-Kähler rotations,
Rotation is
Well, it's maps cohomology to itself.
and that's what you want.
still great.
Yeah.
Think
Well, I mean, whatever. I mean, perhaps there is a shift, but so there is there are strong conditions on this ring for commutative Hyper-Kähler. For commutative Hyper-Kähler manifolds, so for instance, Bogomolov body quadratic form gives some special conditions. So one might expect that if T is HK category, then its Hochschild cohomology shares some properties for classical HK. And the second perhaps thing we might be interested. So I'm just in these properties. I mean, of course, there are much better experts than me on Hyper-Kähler manifolds. So I'm going to talk about very simple properties that I more or less understand. Is the deformation of Hyper-Kähler manifolds. So a deformation, smooth deformation of Hyper-Kähler manifold. So provided that the deformation is projective, is still HK. Also, the question is, since there are some theories for deformation of triangulated category, so if T is a HK category, is the deformation of T still HK. So these more, of course, there are so many other properties of HK manifolds. Some of them you can try to think them algebraically, and you can wonder if they still carry on for the Hyper-Kähler category. So just to discuss these two properties, why this question is not completely trivial. So proving the special properties for the Betti cohomology is done using analytical tools. So if you look at some proofs for whatever properties this may have, usually it uses really analysis, sometimes very strong analysis. And here the question, phenomena are more or less similar. So if I talk about a very small deformation, it's more or less an obvious result, it's completely algebraic. But if you look at long time deformation, this is not anymore a trivial result. It used the holonomy principle, so, which is still an analytic result. So the question to know whether these two results translate into the world of category is not only mimicking the techniques and the proofs that we have, is that really you have to go at a higher, at a more algebraic level for understanding this result. Okay. So this is basically some of the issues I would like to discuss. Probably I won't have time to discuss all of them, but gives an idea of what this theory should be. Well, okay, so now what I will try to do, so if you remember, there was this nice algebra which described what is a Hyper-Kähler manifold. So try to give a category 5 version of this. So unfortunately, I'm not able to give it the complete categorical invariant, but still it relies on some question I would like to highlight. So let's see the Abelian category with a rank function. So of course, the main example I will deal with are C being the category of coherent sheaves on a projective variety, or perhaps coherent sheaf on a projective variety but twisted with a Bauer class. So I look at twisted sheaves, or perhaps coherent sheaves which are G equivariant on X, for G being a linear algebraic group acting on X. Okay. And T is a semi-orthogonal.
What do you mean by a rank function?
Yeah, it's an additive function for exact sequence. So probably I should ask that it is non-trivial or something. Well, let's admit that all of here it's a classical rank function that we know. Well, T is semi-orthogonal component of BBC. So a graded algebra T is said to be homological unit for T. So somehow I'm trying to replicate the definition of the algebra I gave you before in the example for the Hyper-Kähler manifold. So if it is maximal for the following property. And so for all f in T, there exists a morphism of algebra AT inside the graded algebra like this, which is functorial in the way you can imagine. So it means that if I have a morphism between two objects f and f prime, then the morphism induced by the same element will make the obvious commutative square commute. Second property, for all f such that the rank of f is non-zero, this map is injective. Okay, so these are the two properties, and finally I conclude my definition with a last point. F is said to be unitary if AT is equal to the graded algebra. So okay, so this is a rather so I will give examples which are more interesting. So I assume that C is the category of coherent sheaves for X value T. So it's projective if you want. Well, then the trace map going from R and of E to OX gives you exactly
So A is differential then because of the
yeah, indeed. Well, that's
So what is A sub T and A sub sigma?
oh,
It's also
sorry.
T.
No, thank you. That's it. Well, we can discuss that later.
What is F? So F is arbitrary, right?
Yeah, F is arbitrary.
So
So
you were saying that acts from F to F are all the same for rank not equal to 0?
no. But this is
Oh,
separate.
F is unit. Okay.
This is separate. So these are the properties for which the homological unit should be maximal. And I add an extra definition that it is unitary if you. Well, it's just a convenient way to unify many examples which would be cumbersome to unify with notation. So then you see that this is well. So no, there will be still a non-trivial. H star OX is a homological unit for X.
What about the second part of this?
Yes.
Can you just read me the second line?
This one.
Yeah.
So for all F, such that the rank of F is non-zero, then the map here is injective.
So if you take a structure shift for this AT, then it's not logical.
Yeah, structure sheaf is unitary.
Why did you mention trace?
So I mentioned the trace because it proves that it has these properties. Okay, so another example. So expanding this example, we see that if T is a semi-orthogonal component in dBx and OX is in T, then H star OX is again the homological unit for T. Well, now I come to a non-trivial example coming from a semi-orthogonal component. So if X is in P5 is a cubic fourfold, so we know that dBx split as O of 1, O of 2, and T. Well, this category was studied by Kuznetsov, and it looks like the derived category of a K3 surface. And indeed, one can prove that the homological unit for T is Ct divided by G square is T integral. And of course, you notice that this is not at all H star of OX, because X being Fano, its homological unit is only C. So you have, well, I mean, there is not, it's a completely stupid notion, and not smart, but it's just, you see, a convenient way to unify many phenomena, which otherwise would be slightly annoying to say. Well, the last example is that if G acts on X, well, with some properties, then H star OX G is a homological unit for dB to the category of G equivariant coherent sheaves.
This unit is unique.
Yeah, so indeed it's a good question. When you have a unitary object, so by maximality property it is unique. As long as you don't have unitary, I mean, I was not able to find examples where there are no unitary objects. And somehow I think, well, I will say it later, but for, well, I won't show any proofs, but in all proofs I can produce the fact that there are generating families of unitary objects is very important. I mean, it really plays a role. It's like the line bundles on a smooth projective variety.
It's a way of defining Hodge number HI0 of the equivalent function.
Mm-hmm.
It's a way of defining HI0 as
Okay. So the question I would like to ask is when is the homological unit derived invariant? So I will explain. I will spend some time on one special case.
union with fixed rank function.
Yeah, no, indeed. I mean, meaning that it does not depend on the rank function and on the embedding. I mean, on both. Well, of course, one cannot expect. Of course, if I take the rank function being trivial, one cannot expect it. So that's what I said at the beginning, that I should impose some conditions on the rank function. And
then it should be unique, the rank function itself.
I don't know.
Now you have all the differences.
No, on the rank function. And again, so there is an example for which so let's look at phi from dbx1 to dbx2, an equivalence between smooth projective varieties. In particular, a result of Orloff guarantees that it is of the form, it is of Fourier-Mukai type. It means that phi is phi is of this form. I will use it in a minute. So when do we have as a graded one? Well, of course, it's a sub-question of the big problem I mentioned before, is that is the Hodge cohomology a derived invariant? Well, but it seems that this one is still way easier to tackle. So assume that there exists L1, a line bundle, such that phi of L1 is a line bundle. Then, as was mentioned, because line bundles are unitary, then it's obvious that H equal of OX1 is graded isomorphic to this. Well, in fact, one can build a little bit further on this. That now assume that phi of L1, that the rank of phi of L1 as an object of X2 is not 0. Then using the trace map, you see that this, you have an embedding like this, which is an embedding of ring, and it is split. Not split as an embedding of ring, but split as a morphism of graded vector space. Well, and similarly, if you assume furthermore that there exists L2 line bundle such that phi of L2, so it's phi minus 1, so the inverse equivalence is not 0, then you have the converse embedding. And combining the two, you find an equality. So finally, this question about part of the Hodge cohomology reduced to a seemingly much easier question, which is, can we always find the line bundles which image is a non-zero rank? So I'm not able to prove that in general, but I can prove it in many examples. all these examples seem to cover everything we know about, all examples we know about Fourier-Mukai functors which are derived equivalent. So let phi be a derived equivalence between smooth projective varieties. So in particular, as I said, because of a result of Orloff, it is of Fourier-Mukai type. And assume that one of the following conditions hold. So first of all, E is a generically pure sheaf. So by this I mean that on an open subset it is a pure sheaf, possibly shifted. So the Chern class of E are 0 for I equal 0 to dimension of x1 minus 1, which is equal to the dimension of x2. 3, the cohomology rings so the algebraic cohomology rings of x1 and x2 are generated by line bundles. And so for x, dimension of x1 equal 2, and 5 is projective or a spherical twist.
What do you mean generated by line bundles?
So the class of line bundles generated.
Even C1.
Yes, C1.
But it's sort of Hodge conjecture, right?
No. No, it's very specific types of varieties. I mean, this is related, of course, to the Hodge conjecture, but I mean, finding such varieties is very, very special. Well, and so the last condition is then there exists L1 such that phi of L1 has a rank non-zero. So we pick x1, and there exists L2 such that phi minus 1 of L2 has rank non-zero. So just let me quickly comment. So this is the equivalence which come from a universal bundle. So every time you have a moduli space and the space of origin, every time you have a Fourier-Mukai given by the universal bundle, sometimes it might be an equivalence. So this falls under this condition. These conditions are for birational equivalence. So all birational flops, whatever for which we know derived equivalence satisfy this. So these also are related to moduli spaces. So some moduli spaces tend to have this property. So whenever you have an equivalence between moduli space, which has this property. On surface, I don't explain. And the last one is the kind of special transformation we know for Calabi-Yau manifold and Hyper-Kähler manifold. So basically, as far as I know, and perhaps I'm frankly mistaken, but I have the impression that all examples, geometric examples that we know of derived equivalence, they fall under one of these conditions. Okay. Well, of course, I would like to prove it in general.
Just one of them. Just one of the conditions.
Yeah, only one.
I mean, Hodge conjecture is not mostly unknown for products of K3 surfaces, and we have lots of direct equivalence between K3 surfaces and their products. I mean, take like a low did.
Yeah.
You go down curve on K3, you go up, you change it. I mean, you have lots of direct equivalence between K3 and K4.
Yeah.
And then for products of K3, we don't have this Hodge conjecture statement. I mean, the third statement is Hodge conjecture.
No,
It's not Hodge conjecture.
just some statement.
No, it's
So what was your first?
no, it implies what you
But
But we don't know Hodge
It's a generic
conjecture for
and some assumption.
Generically, it's a complex with only one term. The kernel giving the derived equivalence.
It's because
Ah, sorry, yeah, I erased here. The phi is a Fourier-Mukai kernel. Well, so of course I would like to prove it in general, but since I'm not technically able enough to prove it, but of course it would be interesting to have this result in general. Well, there is another special case, which is in fact more a theorem, which is due to Ubrecht and Hyper-Kähler question, which was my original motivation for such a result, is that if you have a derived equivalence between two varieties, if x1 is Hyper-Kähler, then x2 is Hyper-Kähler also. In particular, they have the same homologic volume. Well, this proof is more difficult because it uses a lot of result on the
X1.
yeah, X1. So this result is more difficult because it relies on the properties of the Hodge cohomology of Hyper-Kähler manifold. And of course, so I would like to extend this kind of result in the non-commutative setting. No, but since I don't have all the, I'm not able to prove all the properties that the Hochschild cohomology ring of Hyper-Kähler categories should satisfy, then I'm not able to prove this result in general for triangulated categories. In some sense, it's yeah, this result used a lot, and one would like to dream that one can prove it without using a lot. Okay, so now I can give the definition. So C is an abelian category with rank function. Well, of course, you can think to only the three examples I mentioned before. Is it coherent shifts on projective variety or whatever? And T is a semi-orthogonal component of DDC. So we say that T is Hyper-Kähler of dimension 2m if all the following conditions are satisfied. So T is smooth, compact, admits a strong generator. Well, for all these conditions, if you prefer, you can assume just that T is a semi-orthogonal component of X smooth project. So second condition, the shift by 2m is a self-functor for T. So this is the categorical version of canonical bundle being trivial. Well, and the last condition you might have guessed, if I spoke for almost 45 minutes of homological units, it's to be able to speak about them, is that C T divided by Tm plus 1 is a homological unit for T. Finally, last step is that T admits a generating family of unitary objects. So I think I'm finished. So I will just conclude by one result. Okay, so we have this definition, which one would like to be more invariant, but still, in some cases, it is invariant. Well, and I will go on the construction techniques. So if Y is a rational Gorenstein with omega Y isomorphic to OY and the algebra of OY is C T divided by T m plus 1. So this is typically the case for singular Hyper-Kähler manifolds. On the state module space of sheets on the K3, if they are singular, still they will satisfy this condition. Then a non-commutative quotient resolution of Y is a Hyper-Kähler category. So by non-commutative resolution, I mean that you can write it as dBy AY, where AY is obtained as a push forward of a relative tilting object on a resolution of Y. So of course I don't have any time to explain what I want to mean. But a consequence of this result is that so it was expected by many physicists. I mean, well, for them it was trivial, of course. But I don't think that they had a good language. Well, still I don't have also a very good language, but slightly better than the physicist language. So they wanted to express that if X is Hyper-Kähler and G is a finite group of symplectomorphism. So I mean automorphism which are symplectic on X.
What did you write?
Finite group. Sorry, finite group of symplectomorphisms on X. So by this I mean automorphisms of X which respect the holomorphic symplectic form. Then dB of the stack, dB of this category is HK. Well, I should add that it has a trivial stabilizer generally. Is a HK category. Well, in fact, you can do better. Sorry, you don't assume that it is a finite group, but you assume just that the stabilizer are finite everywhere, and generically they are two. Okay, so this is a version of a result which was a conjecture by, well, not conjecture, which was used by physicists, but at some level of rigor, slightly less than this one. Well, but still, because for them there is the notion of stack, so they can formulate stack. But one question I would like to ask, and I'm finished, is that so O'Grady produced example of singular moduli space. He described in details. So if R is equal to 2, it has a crepant resolution. Which is Hyper-Kähler. So this is O'Grady, one of the O'Grady sporadic examples. And if R is bigger than 3, no commutative crepant. So this is Kaledin, Lens, Orger. And so the question is that if if R is bigger than 3, admits non-commutative crepant resolution. So it is a question. I don't know the answer. Well, in such a case, I think it would be quite interesting because for a long time the example of O'Grady was considered as sporadic, meaning that there is only one. And in fact, if the answer to this question is positive, it means that this example is not at all sporadic. It is, in fact, part of a series which is infinite, but only the first term is commutative, and starting from the second term, they become non-commutative. Okay, so I finished there. I'm sorry. And, thank you.
What are the singularities of the first example in this series?
Of this one?
R equal 3.
It's a double cover of nilpotent orbit of type C, I think.
Of type what?
C.
Of type C?
Yeah.
What does it mean?
It's a nilpotent orbit associated to SPN.
Which one?
The one which gives the correct dimension. I forgot the number. It has dimension 18, I think. So it's well, we can discuss that if you want. It's a double cover which is badly ramified. It's not ramified in a divisor, but it's badly ramified. And yeah.
Any other question? If not, thank you very much.